Hi, and welcome to this video on John Dalton, the scientist who proposed the first cohesive chemical doctrine. Today we'll delve into how people thought about chemicals back in Dalton's day and note his many contributions to science along the way. Dalton began his career as a humble, self-taught schoolmaster in the Lake District of England in the late 1700s. He was a curious and thoughtful man, but given the time period, had no advanced equipment to probe the properties of matter. So he began his career simply by making meteorological observations like wind speed and barometric pressure. As he observed the world around him, he asked questions like, "What's in a cloud? How does water vapor become rain?" While he contemplated these atmospheric questions, his curious mind wanted to probe further, so he wondered, what makes up the water in the water vapor? Let's stop there for a second. At this point in history, scientists weren't sure that atoms even existed. Dalton would come to play a significant role in this later. The law of conservation of mass had just been proposed by Antoine Lavoisier in 1789, meaning that scientists had just realized that mass cannot be created or destroyed during a chemical reaction. Alchemy and the ill-conceived concept of phlogiston were still quite popular. The phlogiston theory postulated that all combustible bodies contained phlogiston, a fire-like element that would be released upon combustion. Scientists during this time were just beginning to understand the nature of the world, and much of it was still a mystery. So as we learn about Dalton's experiments and theories, keep in mind that while they may seem like common sense to us now, what he was proposing was radical for the time. Dalton's extensive study of the atmosphere led him to develop the law of partial pressures, his first major contribution to chemistry and physics. He took note of the atmospheric pressure on normal, dry days. He then observed that on humid days, the atmospheric pressure increased by the pressure of water vapor. In other words, the more H2O was added to the air, the more pressure was added to the air. P humid air equals P dry air plus P water vapor. He generalized this into the law of partial pressures. The total pressure of a system is equal to the sum of partial pressures for each component of the system. P total equals P sub 1 plus P sub 2 plus P sub 3 plus etc. Let's take this balloon, for example. The components that make up the air in the balloon are nitrogen, oxygen, and carbon dioxide. The partial pressures from these components are what determine the total pressure of the air in the balloon. Once chemists realized that the pressure of a gas was directly correlated to the moles of the gas, this law of partial pressures would be recognized as an application of the ideal gas law, but that wasn't conceived until 1834. Dalton also confirmed Charles's law by demonstrating that different gases would expand the same volume over the same increase in temperature. This law is also an application of the ideal gas law credited to Jacques Charles, who had made this discovery in the 1780s, but never published the work. Now let's consider Dalton's atomic theory of matter. By the time he proposed this theory, he was not only theorizing based on his own gas phase experiments, but also the laws put forth by his fellow scientists. These three laws were, number one, the law of mass conservation, which states that the total mass remains constant during a reaction. In other words, you can't create or destroy matter in an isolated system. Number two, the law of definite composition, which states that any sample of a substance, even from different sources, has the same chemical composition. So, for example, the calcium carbonate in marble has the same chemical composition as the calcium carbonate found in coral, though their crystal structure is different. And three, the law of multiple proportions, which states that in different compounds of the same elements, the masses of one element that combine with a fixed mass of the other can be expressed as a ratio of small whole numbers. Let's take a moment to understand that last law because, one, it's a bit confusing without an example, and two, it will play an important role in helping Dalton develop his atomic theory. Imagine you are reacting oxygen with carbon in the early 1800s. You know that carbon and oxygen exist, but have no idea how much each individual atom weighs, or even that there are atoms to be weighed. All you know is the absolute weights of each reactant. First, 100 grams of oxygen reacts with 75.1 grams of carbon. This makes exactly 175.1 grams of carbon oxide 1, a poisonous and flammable gas with a density of 1.25 grams per liter. Next, you adjust your reaction conditions and combine 100 grams of oxygen with 37.6 grams of carbon. This generates 137.6 grams of carbon oxide 2, a benign gas with a density of 1.98 grams per liter, so clearly very different from carbon oxide 1. Now let's apply the law of multiple proportions. First, we can find the ratio of the two elements for both reactions. Let's do some simple division. 100 grams of oxygen over 75.1 grams of carbon give us 1.33 for carbon oxide 1. 100 grams of oxygen over 37.6 grams of carbon gives us 2.66 for carbon oxide 2. 2.66 grams of oxygen per gram of carbon in carbon oxide 2 over 1.33 grams of oxygen per gram of carbon in carbon oxide 1 equals 2 over 1. This illustrates that there is exactly 2 times, not 1.5, not 2.3, but exactly 2 times the amount of oxygen in carbon oxide 2 than in carbon oxide 1. This discovery, along with the other laws mentioned, led Dalton to imagine the nature of matter on the atomic scale. If carbon and oxygen can combine to form 2 different compounds at very specific ratios, there must be some indivisible particle from each element that combines in these very specific ratios. He began drawing images of molecules made of atoms, which could explain the whole number ratios observed in his atomic weight experiments. Here's an image from his publication, New System of Chemical Philosophy. You can see how he began to conceive the atomic world. There are these fundamental particles of each element, the atoms, which then combine to form binary compounds, which themselves have unique properties. The atoms can combine in different ratios to create even more compounds. These pictures provided scientists with the imagery to understand both the simplicity and diversity of the chemical world, as it allowed for infinite combinations of a core set of elements. Dalton laid out his new atomic theory in the following 4 postulates. Number 1, all matter is made of atoms, which are indivisible units of an element that cannot be created or destroyed. Number 2, atoms of an element cannot be converted to a different element. This was a rejection of the still popular theory of alchemy. Number 3, atoms of the same element are all identical and have fixed, unique mass and properties. Number 4, atoms recombine in whole numbers during a chemical reaction to form new compounds, which have fixed fractions of each element. With this atomic theory, chemists had a systematic, universal language that allowed them to describe the results of experiments and the chemical makeup of the world. This era, the late 1700s and early 1800s, marked an important turning point in chemistry. Theories like alchemy and phlogiston lost popularity, and Dalton's cohesive atomic theory gained acceptance. Although there were still those that contested the accuracy of his theory and refused to accept it without direct observations of atoms. And of course, Dalton did make mistakes, and his atomic theory was not entirely correct. He had no way of knowing how many atoms were in a molecule and only made guesses at the ratios. While some were correct, some were wrong. For example, he believed water to be HO, not H2O. He also envisioned the atom as a solid billiard ball, not having any knowledge of subatomic structure. This meant that he could not foresee the existence of isotopes or understand why atoms form the bonds that they do, which requires a thorough knowledge of electronic configurations. And while it's not alchemy, some atoms can decompose or combine to form new elements in nuclear reactions, which he wasn't aware of either. Even with these oversights, Dalton's atomic theory still forms the foundation of our modern chemical knowledge. And just in case you weren't already impressed by Dalton's work, on top of all his contributions to chemistry, he also studied red-green color blindness. He himself was colorblind, as was his brother, leading him to conclude that the condition was hereditary. He was so important to understanding the affliction that it is often still referred to as Daltonism. Okay, let's wrap up with a few review questions. Number 1, which of the following best describes Dalton's law of partial pressures? A, the total pressure of a system will change depending on partial pressures from external elements. B, the total pressure of a system is equal to the sum of partial pressures for each component of the system. C, the total pressure of a system is dependent upon how many components are in the system. Or D, the total pressure of a system is independent of the number of atoms present. The correct answer is B. Adding up the partial pressures of each component in the system will result in the total pressure for that system. Number 2, which of the following is not a part of Dalton's atomic theory? A, atoms recombine in whole numbers during a chemical reaction to form new compounds. B, all matter is made of atoms. C, atoms of the same element are all identical. Or D, atoms of an element can be converted to a different element. The correct answer is D. Dalton theorized that atoms could not be converted to a different atom. The idea that they could was seen in the still popular theory of alchemy, which Dalton rejected. Number 3, which of the following is not something Dalton discovered? A, the law of partial pressure. B, color blindness is hereditary. C, the law of conservation of mass. D, atomic theory. The correct answer is C. Though Dalton used the law in his theorizations, it was discovered by Antoine Lavoisier in 1789. That's all for this review. Thanks for watching, and happy studying.